You can start. Good morning, all. To one and all. So today, we are going to start a session on simulating manufacturing processes using SimFact additive. Okay. So yesterday, I think we had a brief overview of SimFact welding modules and the forming modules, and what are the different processes in which we can simulate the welding and forming processes. And today our topic of discussion will be additive. So I'll just take up my slide for that. So SimFact additive. So again, it is the SimFact that is actually the simulating manufacturing processes, and SimFact additive mainly used for additive manufacturing process actually. Okay, so when I talk about the SimFact additive manufacturing processes, we are talking about basically the metal additive manufacturing processes, basically powder bed fusion process. And inside the powder bed fusion processes, we can simulate processes like selective laser sintering, selective laser melting, and so on and so forth actually. Okay. And if we are, looking at, for example, the powder bed manufacturing processes, we will look at the module called SimFact additive actually. Okay. And if we are, looking at, deposition kind of processes like welding, there is one more module called SimFact metal deposition. It is which is mainly used for processes like direct energy deposition and such kind of processes where we are using arc-based or laser-based heat input to deposit material. That is comes under the SimFact DED module. Okay. So in additive, we are looking at SimFact powder bed fusion actually. Okay, mainly. So a brief overview of the metal additive manufacturing process, mainly the powder bed manufacturing processes. So in powder bed manufacturing processes, the inputs source, mainly most of the time we use laser as an input source for selective laser melting process or direct metal laser sintering process. Okay. And these are mainly different terminologies which is used for this powder bed fusion process actually. Okay, most of them are almost, I mean, even though the names are same, the technology behind is almost the same only. So based on different companies who develop these kind of processes, mainly broadly it is known as powder bed fusion processes, but laser-based processes can be known as these kind of names actually, like selective laser melting (SLM) or direct metal laser sintering, which is known as DMLS. Okay, and some machines are there which are known as EBM, where they use electron beam. Actually, it is called electron beam melting edge, EBM machines. Okay, so these are very rare, where they use electron beam to melt the metal powder. Most of the time, we see that we use laser-based technologies to do that actually. So here we can see a brief overview of how the process happens actually. Okay, so there are a lot of players in the industry like EOS and we can say such kind of machine manufacturers who manufacture these kind of machines, which is nothing but which is for the powder bed fusion technologies actually. Okay, so basically what will happen is like there will be something like a metal powder. It can be titanium, it can be aluminum-based alloys, or it can be Inconel, such kind of powders. And mainly these kind of manufacturing processes are prevalent in the aerospace industries actually. Okay, so mainly what they do is here they have a powder. You can say a delivery system will be there, where there will be a recoater like this. The recoater will there will be a delivery system where the piston or this mechanism will move up, and a reporter will supply the powder to this particular the chamber actually. Okay. Then the powder will be laid on this chamber, and the laser will come and melt the particular location or the process, a particular portion, so that the part there will get melted. And subsequently, another, layer of powder will be supplied by the recoater onto this particular location. Likewise, as and when the laser melts this region, a particular, you can see here, the particular, layer will be melted on a particular zone, on a particular region over here. And then what will happen is this, chamber, this thing will go down. And then again, one more layer of powder will be laid. And again, it will be subsequently melted. Subsequently, you can see as it goes down and gets melted, the parts will get manufactured in this fashion. Okay. And there will be a part that is getting manufactured over here, layer by layer. Okay. So one layer will be very thin layer of material, like it will be around 30 microns to 50 microns of thin layer will be laid by the recoater to perform this operation actually. Okay. So this is a general framework of how the manufacturing process happens. And generally, this particular process uses the laser heat source actually. So there will be a laser which supplies the heat source and then melts the powder at that particular region. Okay. So the machine will be, suppose how this, model is supplied to the machine is through a slicing software will be there in the machine, which slices your CAD model into several layers. So there will be around, if you take, 100 layer or 100 height of this particular component, there will be around, like say 100 to 150 layers of slicing will be done by the software. And each slice will be there like this actually. Okay, so the machine will read each slice, then the powder will be laid on this. The laser will melt that region according to the information that we are giving to the machine. And then the parts gets manufactured actually in this fashion. Okay. So this is the powder bed fusion method actually. Okay. So this is one kind of additive manufacturing method, which is very prevalent in the aerospace industries and some of the automotive industries as well. They manufacture parts with this method actually.
Why it is particularly for aerospace? Is there any advantage for that?
Yes, sir. So this particular, additive manufacturing is something like it is opposite of our subtractive manufacturing process, like milling or where we take away the material. Okay. Here, what is happening is additive manufacturing. Instead of taking away the material, we are adding the material actually. And one more advantage is that we can make intricate shapes that might be, needed in the aerospace industries, where nowadays a lot of optimization and weight reduction is happening in the industry. So using conventional methods, we may not be able to manufacture components which are possible in additive manufacturing, like this method set. So that is one reason why they
are they using for the functional part, functional purpose only, or prototype part still?
Most of it is in the research areas, but these, you can say sometimes kind of nozzles and things like this, conical structures, those kind of things they are manufacturing using the additive.
It's for the final use purpose.
Yes.
Not for photo purpose.
Yes. So one more method is coming up for deposition kind of methods using arc-based laser beam methods. That is called, you can say the DED method actually, direct energy deposition. So here we can use, laser-based or arc-based heat sources to deposit material, okay, onto the base plate actually. So there will be a base plate on which the part will be manufactured actually. Okay. So it might be a powder-based or wire-based, where the material is fed, into the zone, and then the material is like a, welding simulation itself or welding process itself, the material will be laid layer by layer actually. Okay. So this can be simulated in our welding software, like we saw yesterday. Likewise, we can go on, depositing the material layer by layer. And there is a, in the Simufac welding, there is a direct energy deposition module where you can easily define your, trajectories, your path to build component layer by layer. Okay, so it might be done by robots, layer by layer deposition, and there might be trajectories of these robots actually to build a particular, profile. So all these things we can feed it in the software, and we can simulate such kind of, deposition kind of methods actually. So this is a brief overview of what is, possible in the Simufac additive manufacturing modules actually. So coming to the powder-based method. So here you can see in our previous slide, we already saw how this happens actually, how this layer by layer happens. So what will happen is the laser will be there, which will move in a particular pattern to, create this layer by layer, profiles on this particular powder layer actually. Okay, so you can see when the laser comes and hits the powder layer, it will solidify the layer actually. Okay, there will be a melt pool. So we can consider this as like a micro welding actually, where a small area of the part is melted, and then the laser beam travels at a particular, it has a particular velocity by which it travels, and then it will melt the subsequent layers of powder actually. Okay, so these powders are very small, like very small granules of powder. And there are some manufacturing methods to create this powder, metal powders actually. It can be titanium. Most of the industries use aerospace use titanium material in a very, very wide way actually. Okay. Other than titanium, there are inconel materials that are used, and aluminum alloys. Those kind of materials are used for this particular application section. Okay. So what will happen is in this powder bed, the part descends. Okay, as and when the laser comes and melts the part, a sudden cooling will happen at these areas, and then it solidifies that particular area, and this area will come down actually. So the part will descend, and fresh powder layer will be spread by the recoater. So this is a recoater actually. Okay, the recoater will move and it will spread the powder actually. Okay. Then one layer of powder might be something like 52 micron per layer. Okay. And something like a micro welding process results in significant distortion and residual stress. So this also results in significant distortions and residual stress because there is a sudden heating of the powder, then there is melting of the powder, then there is solidification happening. So a lot of things happen, thermal wise and metallurgical wise. A lot of things happen during the process. So this enables to creation of parts that are not feasible with traditional manufacturing. So that is one advantage of using the additive manufacturing and why it is becoming prevalent in the manufacturing industry. Okay. So here you can see additive manufacturing is also called as a rapid prototyping. Okay, and making small batches of parts. Okay, so we can see parts like these, which cannot be mainly manufactured using such kind of lattice structures, and these kind of parts, which cannot be manufactured using conventional methods, can be manufactured using the additive manufacturing. And if you're doing some kind of optimization like this, for example, this is the part where you want to reduce the weight of the part and make a new design like this actually. Okay. So these kind of designs, it is very difficult to create using the conventional method or material removal methods. It is very difficult to manufacture like this, where we can use or we can look at such kind of technologies where we can build parts like this actually. Okay. So design, mainly what we are trying to do, we are designing parts that would be otherwise be impossible to manufacture. And, it results in lower material usage. So once we are optimizing the parts like this, it will result in weight reduction as well as lower material usage actually, either by design or because of less wastage of the material. So in traditional manufacturing, we are removing the material from the existing material. So that results in a lot of scrap and lot of material wastage. So here we are building the material actually. So we are, building the material layer by layer. So it is something like a additively we are manufacturing this component so that the material wastage is minimal actually. Okay. And lower energy usage. For example, eliminate the production step, no energy usage for removal or material. So there can be, energy efficiency as well, where we don't have to use machines to, or, milling machines to remove this material or any kind of energy requirement is very less. Actually. And another advantage is lightweighting. Lightweighting in the sense that we are trying to reduce the weight optimization or such kind of things, where we are looking at reducing the weight of the components, making the components lighter in, function, means in, you can say in functioning parts where we want to optimize your weight of your components. It can be some automotive parts or aerospace parts that can be used for lightweighting actually. Okay. And manufacturing assemblies without the need to assemble multiple parts, reducing inventory. Like we can manufacture parts without needing to assemble parts actually. So parts can be manufactured in a way it can be together, where you can avoid assemblies and things like that actually. And no need of tooling, because tooling will be prevalent in our subtractive manufacturing process. Here there will be no need of tooling, but some post-processing process will be required after the manufacturing is done. That is a different this thing. Yeah, that will be there, but tooling and things like that can be minimized. Then agility to manufacture parts anywhere, print on demand, and customization. Like we can manufacture parts anywhere and print on demand. We can means we can design our own parts as per our requirement, and we can send it to the 3D printer to print the components. Okay. But as it is prevalent in another manufacturing process, if you take welding or forming, any manufacturing processes, in additive manufacturing also in industries, there are some pain points actually. Okay, especially in the PBF AM processes. PBF means powder bed fusion additive manufacturing process. So here we can see, I can say this is a titanium TI6ALV4 bicycle frame section, which is manufactured actually, okay, using the additive manufacturing. So here what we can see is sometimes when we manufacture this type of components using the additive manufacturing technologies, there can be something like parts may go out of the tolerance, something like this. So you can see the circular, this is the expected tolerance, but it has gone out of the tolerance actually. Okay. And sometimes when you build these parts, we take the help of these supporting structures. So these support structures are holding the part during the manufacture, because we have to manufacture these parts in the machine. In the machine, there will be a base plate on which this part will be manufactured layer by layer. So on this part, we have to keep this part in different orientations, different angles to manufacture actually. Okay, so we can't place the part simply like this as it manufactures. We have to take help of these things called support structures, which will be attached to the base plate along with the part actually. Okay. So these support structures also are a part of the manufacturing process. They are also built along with the part. Later they are removed by some processes. Like you can use some tools to remove these parts, and we cut it from the base plate. So such kind of operations are done to remove these support structures from the the parent part actually, whatever part we are manufacturing. So sometimes what will happen is this support structures can it can separate from the part actually due to some heat induced effects, as well as some induced effects. These can separate from the part due to some residual stresses that can concentrate at these regions actually. So these kind of effects can we simulate in the simulation, and can we, reduce our defects in these kind of parts actually. Okay. So mainly the challenge that they face is distortion due to part dimensions and parts going out of tolerance. And there will be and another challenge will be collision with the recoater blade. So I showed in the previous slide where there will be a recoater which will come and it will deposit the material on this location actually on this particular base plate. So what will happen is if there is a huge distortion, let's say in the vertical direction, what will happen is this part will be the laser will come and melt the part here, but there will be solidification happening here. Then there will be a solid material which is there actually. Okay, so if there is a lot of distortion in the vertical direction, what will happen is the recoater will come and hit this particular part, which can cause something called recoater jam in the machine. And the part might fail because of the recoater coming and hitting the part actually. Okay. So most of the machine they have programmed in such a way that whenever they find that the recoater there is a chance of recoater jam, the machine will stop and the manufacturing process will halt there. It will not go further. Okay. So what will happen is there is a lot of material wastage. Whatever how much ever material you manufactured, that will go for a waste actually. Okay, so that effect is called as a recoater collision or recoater jam, what they call. So this can be a very disturbing in the powder bed manufacturing process. To overcome this, there are some methods in the simulation where we can simulate and check whether the recoater blade there is a chance of a part getting recoater jam and the process getting incomplete actually. Okay. Then there are the residual stress effects that is build abortion, like due to this, cracks can happen between the support structure and the components, or brittle cracks can form in the parts as well during the manufacturing. Okay, so that can result in part or support structures cracking. Okay. So drives distortion in post-processing steps and part fails in service actually. So when the parts, if it is fails in service, there is a lot of material wastage. If you take titanium materials or titanium powders, which are used for manufacturing these kind of components, it is very costly actually. So it is very, cost-inducing process, as well as the machines are also like very, costly machines, what they use these kind of things. So using simulations, we can predict these kind of effects which might happen in the real manufacturing process. So that is the advantage of using simulation technologies like these technologies. And sometimes these kind of, it will halt the productivity, speed, and repeatability in the analysis or in the, production process. And you can see, it may affect the quality of production, like some defects might be there. Okay, these kind of things which can be analyzed. So what are the implications of these kind of methods? Like you can say iterative trial and error, it is required. So if you are manufacturing these kind of components for the first time, you may have to do different trial and errors to get your, components manufactured. You have to, do different trials, which is the effective, which is the right orientation to manufacture this part, and which are the right process parameters that you have to put to manufacture it within this tolerances, and which, can cause high cost in time and resources actually. So making these kind of prototypes involves material as well as material utilization and time. So these kind of things are iterative in process actually. Okay, most of it is in something like a trial and error is required. So this trial and error can be reduced by the simulation. So that is where the need of the simulation comes into picture. Okay. So AM workflow, like additive manufacturing workflow, how it happens is, for example, you have a design, for example, which is shown. It is something like you can say it might be automotive. In this case, it is a race car, this thing, wheel hub. So which is, there in this race car section. So for example, you have a design, then you make the CAD model of this design. You, feed it to the additive manufacturing machine. So there will be a slicing software which will slice your part into different slices actually. Okay. So each slice will be fed into the machine as an information of how the laser has to melt that particular region actually. Okay. Then there is a base plate in the machine on which the part is built along with the support structures like this. So these are the support structures and this is the part which you get built actually. Okay. So once you build it, you will, check for any cracks or anything can form. For example, here you can see some delamination kind of thing happening and the part is getting separated from the support structure actually. Then what you do is you inspect the, part that you built. Inspects for any cracks or any failures or anything is such using some machines. You try to scan the part, you find any, cracks are there or any defect is there. Such kind of things, you try to inspect it actually. So if you find something like a inspection, then what you do is you go back, for example, you inspect the part, you find some, a crack or something in the part. What you do is you have to go back to the initial design. If it is a design modification, you have to write from the CAD, you have to make changes in your design, then come back, build again, then again check actually. So this is a repetitive process that happens actually. Okay. Yes, same effect. So that this is build which is happening in the machine without the software. Okay, that we have not used the software as of now. This is a workflow which they are following in a day-to-day basis actually. Okay. So now we will include the SimFact simulation. Okay. So next slide, what I'll show is in between the build and the design, we have the simulation, AM simulation. Okay. So in AM simulation, before the build, we simulate it. Okay. And check whether these kind of defects can happen during the build actually. So you will get an idea before you actually manufacture the part. You simulate the, in your virtual environment, you simulate this component. You check whether these kind of manufacturing process are going to happen or not actually. Okay, so this will give you an idea of whether these kind of issues will happen so that you don't have to go further. You can go back here, modify your design, then again simulate and check. If you're okay with it, then you give for the printing actually. Okay. Then you give for the printing, then you come out with your, appropriate component after this manufacturing is done. So this will reduce most of your trial and error, which is used for, the printing the part.
Any kind of projects making this build.
Yes, sir.
Actually, if you're a conventional thing, you'll just make a product and you'll just go for machining.
Yes, yes.
So here you're doing this build. Any kind of flaws or that maybe there will be possibility of.
Yeah, there can be possibilities. If there is a, laser is not melting at a particular region, there can be lack of fusion at that region actually. So that may cause some defects. So there are some, machines which can detect those, defects actually. That is manufacturing defects. If you have those kind of manufacturing defects, we have to go back to the, machine manufacturer. We have to tell them that there is a, so they will calibrate the laser according to the this thing actually, so that it will fuse the metal properly, and then it will build your part. And then one more manufacturing defects that can cause is shrink lines and things like that. That is one more effect that can happen. So after this manufacturing process, what they do is they do some kind of heat treatments to relieve your residual stresses and things like that. Then only they will take it to the next process actually. Okay, so there are some intermediate process that happens in the actual manufacturing. Okay, so that I'll show you in the maybe in the coming slide. You can see here. This is the workflow, actual workflow, where your 3D model drawing and the bill of material, everything will be done here. Then the job preparation will be done actually. Okay, job preparation in the sense you will decide where is your support structures need to be. Suppose if you are manufacturing the part like this, or if you keep it like this, whether you will get lesser distortion. So then the part will, if it is oriented like this to your base plate, you have to build support structures. You have to design your support structures which will connect your part to the base plate actually. Okay, so that support structure design is done by special softwares, like there is a Magic software. Magix, it's called as Magix. So that software is done to create your support structures. And in Simufact also, you can create the support structures. You can import support structures from other softwares like Magix into Simufact as well. Okay. So that kind of capability is there. So once you have designed your, support structures in the Magic softwares, and once you design your part, that is the actual component, you send it to the 3D printing machine actually, okay, for the SLM printing. Then the parts will get printed in the 3D printing machine, okay. Then there will be a stress relief heat treatment will be done for those machines. In case after the components are manufactured along with the base plate, the base plate will be removed entirely from the machine. So the part will be there, the powder, extra powder is there, that also will be removed. Then the part will be attached to the base plate actually. Then what you do is, along with the base plate, you can do the heat treatment. They do the heat treatment for the, they relieve all the residual stresses that is happening due to the heating actually. Then they remove the support structures. Okay, like that, these support structures are removed using some technologies like wire cutting technologies or EDM wire cutting technologies, where they remove the support structures from the base plate. Then they use specific methods, like you can use like player-like things to remove the support structures actually. Okay, that manual methods are there, which is coming under the support removal actually. Okay, then they smoothen the parts using the sandblasting techniques. So the parts will not be smooth. It will be having some kind of this thing actually.
Works for complicated like kind of
Yeah.
Like intermediate will be there.
Yes, yes.
If it comes for outer things, that's fine.
Yes.
How about the-
For that, I think specialized technologies are there for lattice structures. Maybe some kind of first of all, and further things are done like isostatic pressing kind of things. So such kind of things are there done for some intricate structures actually. So for those intricate structures, some specific technologies are there to remove it and to polish it so that it will be smoothened actually, those surfaces. And after this blasting is done, still some isostatic pressing is done. Okay, suppose these parts are manufactured, you have to densify those parts because the relative densities will be reduced because of the powder getting melted. So there are specific methods where we can press isostatic pressure, where we apply temperature and pressure to densify the part, to increase its density. Okay, that is called isostatic pressure. So this also can be simulated in the Simufact additive. Okay, then some machining will be done, polishing, and penetrant testing. Okay, all these things are final inspections will be done, marking. So these are all post-processing options that are done actually. Okay, so what we mainly do in additive, coming to our simulation is this part. That is, after you design the part, okay, you do the manufacturing process of this. Then you do the heat treatment. Then you are cutting of the support structures from the base plate and from the component. And hip is nothing but hot isostatic pressing. Okay, these up to this we can simulate it in the software actually. Okay, rest of it machining we will not be doing in the software, or something like you can say stress analysis or fatigue analysis. Later, what we have to do, that we will not be doing here in this software. We'll be doing only the manufacturing process, finding any defects or anything like that, distortions, residual stress. Only that we will be doing in the software.
During that process, we'll check that the intended design is unchanged, dimensional.
Yes, sir. Yes,
Is that-
we can. Yes, we can check that. So that is done in our in this part actually, additive manufacturing part, where we will check whether the manufactured part is going out of the tolerance. So there is something called distortion compensation. So we will take our initial CAD design and we will superimpose our manufactured part onto the CAD. And we will check how much deviation is there within the CAD and the manufactured part.
I wanted to understand whether
Yeah.
after treatment and you have got, that's where you are going to compress it, right?
Correct, correct.
It is possible you are going to compress it.
Correct, correct. Yes.
Then heat treatment is also there.
Yes.
Some amount of distortion, some amount of sizing is also going to happen.
Yes, yes. So that time, what we can do is we can take the end result. We can compare with the initial CAD. Okay. So then we do something called compensation. So we go back to our CAD, do some compensation, and then we manufacture so that at the end of manufacturing with all these kind of effects, you will get the correct manufactured part within the tolerance. I'll show you that in the upcoming slides. Okay. So effect of distortion, residual stress. So each step can have a significant influence. So each step, that is a manufacturing step, heat treatment step, this cutting and all these different steps can have significant influence on these distortions actually, or tolerances, part going out of tolerances. So each step will have a significant influence on these things. Sequence of step matters, like sequence of these steps also matters actually. For example, after manufacturing, if you're doing the heat treatment, the effect might be slightly different if you cut it and then do the heat treatment. Because if you cut it, the residual stresses are there on the part, which can cause huge deflection in the part actually. So normally what they do is they heat the part along with the base plate and then do the heat treatment, rather than removing the material from the base plate and then doing the heat treatment. Okay, so that sequence of steps also matters. Considering the build without post-processing only part of the picture. So considering the build without the post-processing, like post-processing in the sense after the the heat treatment is done, the cutting, this thing, everything is done. So with the build without these process, cutting process, everything, you cannot determine what is the real effect on the component. Okay, so that is something like post-processing. Post-processing is nothing but all your support removal, everything. These stages are nothing but your post-processing stages actually. Okay, after the part is manufactured. So analysis wise, in the numerical or method, we have different scales and in which we can analyze the this method actually. That is, we can do the analysis in different scales. Okay. So first scale will be a macro scale where we can use something called, this is something like a mechanical analysis actually. Okay, where we you can see the animation over here where we are depositing the material layer by layer. So there will be something like inherent strains, okay, which are developed on the part. Whenever we are building a part like this, we can see there will be a lot of effects due to the thermal strains, which are due to the heating of the laser. And then there can be metallurgical aspect. Due to the metallurgical, there can be due to strains due to that actually. Okay. So all these strains combined will be known as these inherent strains. This can be calculated by a method called calibration inside the software. Okay. So we calculate the inherent strains and then we use the inherent strains to build the part like this actually. Okay. That is called as the macro scale method. I'll explain you in detail how to do this method. This will deliver distortion and stress. Okay, we can get the distortion and stress. It's a very effective method where we can, if you are interested in distortion and stresses on the part, we can use this method to analyze your components. Very, less time consuming method and very effective method actually. Okay. Then there is a mesoscale method. So mesoscale method will be useful if you want to know the temperature profile, like what is the temperature that is getting incurred in each and every layer of your part. Okay, so if there is a thermal study involved, we can go with the mesoscale method actually. Okay, so you can see element layer analyzed in one step by hatching segments thermal, mechanical, or thermomechanically coupled. So you can use thermal method, mechanical method, or thermomechanically coupled method to perform this kind of analysis, able to deliver approximate thermal history and derived result. Okay. So normally we do these two methods in the SIMUFACT additive method. And there is one more method called moving heat source method, which is nothing but like a welding what we do, where we, exactly try to capture the, the movement of these lasers like this. Okay. So this can be done only at a very small part level. If you take a entire big part like this method won't be feasible because each and every layer of the laser you will not be able to simulate. It will take a lot of time to simulate actually. Okay. So that's why they have arrived at these two methods, which can be, simulated in a very less amount of time, as well as we will get some using some calibration. We'll be able to match the, real life, results up to a certain extent actually. Okay. So this is called the micro scale, meso scale, and the macro scale methods, which are used in the simulations basically. So coming to the macro scale approach. So macro scale approach, as I told, it's a mechanical approach where we can find, things called, we can find something called inherent strains. Inherent means strains which are inherent in the material. Okay. Material can be different materials that we use. It can be titanium material, it can be a inconel material, such kind of material. So each and every material has its own properties. Okay. When we melt that material, it will have its own kind of strains, plastic strains, thermal strains, creep strains, phase transformation strains. Okay. These kind of things can happen in the material. It is very specific to a particular grade of material or particular type of material actually. Okay. And it varies from material to material. Okay. And it varies from the machine parameters that we're using. It depends on the laser power. It depends on the laser beam velocity. It depends on the hatching pattern that we are using. So each machine manufacturer, they'll have a specific parameter which they would have set inside the machine to manufacture the components actually. So according to that, these strains will be developed inside the part. Okay. So what they do generally in the manufacturing processes, they build these kind of coupons. So these are something like a cantilever coupons that they build. So these are something like we are building these coupons to understand the strain behavior of this particular material. Okay, how the strains will be there for this particular material, for this particular machine parameters that we are trying to use. Okay, so this kind of the strains, it reflects the material, manufacturing parameter, and the machine. Okay, so different machine manufacturers will be having different manufacturing parameters. So these strains will be varying according to that. Okay. So what they do is they build this. This is known as cantilever. There will be a specific dimension to this, which is industrial standards. They build these cantilever samples like this. Then what they do is they will build at different directions, like X, Y, Z direction, as it is shown here actually. Okay, because this can be very orthotropic in nature. Because when we build the materials in different directions, it is not isotropic in nature actually. It is orthotropic in nature. Properties can vary in different directions. Okay. So what they do is they build materials in 0, 90 degrees, and different angles they build these materials. They cut this cantilever samples like this. Okay, which can be simulated using the SIMUFACT. So this shows a simulated one, and this shows a real samples that they have manufactured in the machine. So once you cut it, okay, what you can do is you can measure the deviations. Once you cut, what will happen is due to the strains which are developed in the part, it will lift up actually. The part will lift up due to the strain developed in the part. So those strains are known as inherent strains actually. Okay. So what they do is they measure this, at the tip of this cantilever, they measure this. And at the same time, they use all the same parameters, same material, everything in the SIMUFACT additive. They simulate the same thing in the SIMUFACT additive also. Then they will compare the distortion the displacement we are getting in the simifact additive and in the real part. Obviously, there will be some deviation. Okay, because we cannot capture all the parameters, machine parameters that we are using in the simulation actually. Okay, there will be some kind of deviation that is happening. So how to reduce this deviation and how to arrive at a strains which is close to your real life manufacturing component actually. Okay, that is the idea of doing this kind of calibration process where we are back calculate. We are comparing the distortion. We back calculate the strains and we calibrate the strains so that it will come close to our manufactured sample actually. Once you get the strains, you can use the strain for your real manufacturing part. The part can be any part, any shape, anything. But the thing is that it should be of the same material which we used for the calibration. It should be the same manufacturing parameter which you used for the calibration. And you should be, it should be the same machine, which was used for the calibration actually. Okay. Because if your machine changes also, sometimes what will happen is they would have changed some laser parameter or anything. That will again change the strains which are developed in the part. So what they do is generally they do this particular exercise to calculate the inherent strains. You save this inherent strains in your database and then you can use this strains for your real manufactured part. So for example, your part will be something like this where you want to manufacture. Okay, you can use the inherent strains for your real part. You can build your part and check all this distortion, residual stresses that can be built on the part actually. Inherent strains is a very good method. Other than an inherent strain, one thing in inherent strain method is or mechanical approaches, we will not be able to get the thermal history on the part because we are indirectly all the thermal aspect we are taking it in the calibration, and we don't use any thermal things in the because we already calculate the strains from the calibration. We just put the strains in our model and then we perform the mechanical analysis. So we don't get any thermal history that is going on in the part. If you want to study the thermal history, we can use the thermomechanical approach. Okay, where we get the distortion, stress, peak temperature, heat flux, just like a welding analysis. We can get all these results in the thermomechanical approach. But what is the disadvantage of this thermomechanical approach? It is very slow because it has to calculate the thermal strains. It has to put the thermal strains into the mechanical, analysis, and then calculate strains, mechanical strains, then distortion and stress. So it will be a time-consuming process. This one. That's why if in some cases we will avoid the thermomechanical approach for additive manufacturing process. We follow the inherent strain approach most of the time. Okay. So this shows building of the part. Like you can see in the software, how it looks like is we create the mesh of the part, something like this. We bring in the scan part from your machine, or you can get the CAD part from your CAD software. We mesh this part like this. So the mesh is called as this kind of brick kind of mesh, like hex meshes that we saw yesterday. So these meshes are called, you can say voxel meshes actually. Okay, voxel mesh, where the mesh will be done on the part. The variables will be calculated in the mesh and it will be mapped onto your part at the end of the analysis. Actually. Okay, mapped onto the the surface. So that kind of technology is called voxel mesh technology, which is there, which is used most of these manufacturing solution. They are using this kind of technology to capture the variables onto your structure actually. Okay. So this shows an animation of how the component is built inside the part. So it will be layer by layer. The voxel material, the mesh will be deposited layer by layer. The distortion, everything will be captured. At the end of it, it will be mapped onto your surface actually, whatever surface what we are trying to input it. And heat treatment can be done. Stress relief heat treatment. Normally, they do the heat treatment to relieve your residual stresses. So you can see the part after it is manufactured. A lot of stresses can be built, and after you relieve your stresses, you can get the part which is free of your residual stresses, which is ready for the subsequent process like support removal and things like that, so that it will not cause any kind of damage to the part due to residual stresses. Okay. So you can give the, you can see the temperature versus the time cycles. You can define your heating rate, then the subsequent stage, and then the cooling can be given as a table here to simulate your heat treatment process actually. Okay. So heat treatment can cause additional distortion in the parts. So this kind of effects can be captured. Then the temperature or time defined by the table. Temperature dependent material properties like elastic modulus, all these things will be given into the material properties. So these things effects are taken care actually. Okay. Temperature related thermal conductivity properties, specific heat and conductivity. These kind of things will be taken care during the analysis. And so in the, for the heat treatment, we may require some creep properties. So there are some creep laws which are there in the material properties, where we are using these kind of, equations to calculate you can say the residual stresses, the stress relief, for the stress relief, for relieving the stresses, these kind of creep laws or material properties will be required to capture these kind of effects. Okay. So this is inbuilt in the software. What equations they will use, it is shown here. And then comes cutting and removing. So cutting and removing is a important process. So you can see the animation here where the part is cut from the base plate and the supports are removed actually. So incremental cutting process can be simulated here in the SimuFact. Your direction of cutting and the length, the length from where you are cutting the part. Okay, all these things can be simulated in a step-by-step manner in the SimuFact software, where we have different tools to cut the support structures. And if you want incremental removal of the support structures, we can do that step by step to get the final component. So the support structure removal also, it will be a major factor in determining the end distortion of your component. Okay. So stepwise cutting is available, like incremental, then support structure removal, individual removal. For example, at a particular region, you want to remove support structure in the beginning. Then after that, you want to remove in a subsequent region. So that kind of thing, we can define it in the software individually. Like that kind of flexibility is given for the support structure removal actually. And then comes hot isostatic pressing. So this kind of, it is very rarely done in the this thing in India, but in outside India, they do these kind of pressing processes where you want to densify the part. Like most of these parts are not, the relative density will be very low actually. Okay, so to densify this part, they do something called HIP, that is known as hot isostatic pressing. In the HIP process, the part will be kept in a hot isostatic pressing this machine, and there will be a temperature and pressure applied over time actually. Okay, so then what will happen is, due to that effect, the relative density of this part will increase. Okay, which will make your part more, means it will improve your properties of your part for the further functioning of the part. So temperature dependent material properties, all these things, you can see the densification laws are applied to the, in the mesh, and then we can calculate how we can increase the relative density. Okay, for example, if 20% pressure is applied, what is the relative density? We can see it on the part actually. And after the 100% pressure is applied, what is the relative density on the part? So this kind of simulations can be done with respect to the hot isostatic pressing. Then comes optimal, you can say, build orientation and things like that. So if you are building your part, like if you are building the part vertically, what can be the end effect of that? If you are keeping it horizontally, will it be better or not? Okay, these kind of things we can study actually. So if you are building the part vertically, we can see it has some sort of distortion which is happening here. Okay, that can be avoided if you are building the same part in a horizontal position inside the machine actually. So this kind of things we can simulate it and check before we actually go for a part manufacturing. Then comes support structure. So support structures are things which are built along with the part. Okay, so then we can also see if you inside the support structure, you can see there are some support structures that are there on the part, and we manufacture this part, and you can see there is some distortions which are coming in the below part. So do we need to use more support structures to reduce that distortion? Or should we optimize the support structure or we are using more support structures such that we want to reduce the support structures and save the material? Okay, that can be another study. So these kind of studies can be done using the support structure optimization tool is available inside the SIMUFAC, where we can optimize the amount of support structures for the simulation. So that will, you can simulate it and you can check whether you will be able to get the part in the right at the first time before we go for a print. Then there can be distortion effects. Like if you print the part like this, after the heat treatment, what is the distortion? After you cut from the base plate, what is the distortion? Then after you remove the support structures, you will get the end distortion. So this will be an incremental process where it happens, where at the stage by stage, you can see your results at each and every operation. Okay. Then there'll be stress, same with respect to distortion, they have shown with respect to the stress also. Like after heat treatment, you can see some residual stresses that are getting built in the part. After you do, if you don't remove the residual stresses, it can cause, damage in the part when we are cutting it from the base plate, or if you are removing the, you can say the support structures from the component, it can cause some problems. So these kind of things can be studied. So individual stages for optimizing your result. Okay, it can be with respect to build orientation, support structure, density, or machine parameters, stress relief, cutting and support removal, or hot isostatic pressing. So these are all the different stages by which we can analyze this part. So despite best efforts, we can say still we might face distortion, maybe out of tolerance with all these efforts. So there is something called to counter, overcome these kind of things. There is one more thing that we can do, which is known as distortion compensation. Okay. So in what is distortion compensation? Like how it will, help the user to overcome distortions. So the user can export compensated STL file, or you can say the file from the GUI, simulate to verify resulting compensation, yields the desired geometry, send compensation STL AM machine for physical build, which means that at the first level, let's say we are initially building the geometry with support structures. We analyzed the part, and let's say we are getting some deviation. So here you can see some deviation of the part which is happening. At the, you can say at the end, I can see some deviations happening at the end. So how we can overcome this deviation so that at the end of it, you will be able to manufacture the part within the tolerance. Okay. So they do something called compensation. Compensation in the sense that we pre-compensate the part before the build. Okay. Pre-compensate the part in the sense we make some changes in the geometry such that after the build, the geometry will be in the right tolerance actually. For example, you can see compensated STL shown by offset. We can give so there are some optimization algorithm in the software where it will do some optimization in the part shape actually. Okay, so that you will get a shape in such a way that you build this part, at the end of it, you should be able to get the correct shape in the machine actually. Okay, so that is called distortion compensation. Okay, very widely used in the AM industry. So this shows a simulation of an impeller blade. So this you can see some thin components which are using the additive manufacturing, and this is an impeller blade thing. This shows the process how it is manufactured, and this shows the simulation how we can do the simulation of these similar components actually. Okay. So you can see different process that has been happening. So you can see the, after the build is done, there is stresses are captured, and then the cutting is done here from the base plate. Then the support structures will be removed. You will get the end component like this. Okay. Some case studies. Coming to some case studies where they have used such technologies to build some components actually. So if you see this part, it's a case study of a light hinge. That is this is a car hood where they keep these light hinge parts actually. Okay, so this is mainly used for passenger safety. I'll show you in the next slide how it functions actually. Okay, but before that, you can see the conventional part, which looks something like this. Okay, so this is something like they wanted to reduce the weight of this component, and manufacturing component, end manufacturing goal was to get a design something like this. Okay, which should perform the same work that this was doing. At the same time, it should be able to withstand the loads and things like that, which is there in this component actually. As well as we should be able to reduce the weight of the component. Okay. So there are different topology optimization tools are there, which are there in the field of simulations, where we can get optimized designs like this actually. Okay. But you can get the optimized design, but whether it will perform or not, that is another question. Okay, whether it will whether we can manufacture first of all, we cannot manufacture these components in a traditional ways. That is another challenge. So then this is where we use the additive manufacturing technologies to build parts like these, so that we can optimize your weight, as well as you can reduce the material utilization also actually. So you can see the weight saving more than 70% from 3.3 kg to below 1 kg, so that you can have a greater than 2 kg you can say savings with respect to your weight. And this particular engine hood hinge, it was built by this particular build on this particular material, that is 316L stainless steel material actually. So this particular component is used for pedestrian protection. Okay, and there will be a cable bracket which will be functionally included with these parts, and parts get reduced from 38 to 6. For example, there are different parts are there to where these parts are assembled to form these kind of components. But you can see in additive manufacturing, we can reduce the number of parts also, like connections parts also we can reduce to build these kind of components. So this was done by Simufact in partnership with companies like ENGG and Goldspine Technologies to build these kind of parts actually.
What is the light hinge actually?
Light hinge I'll show you here. So this is something like this. You can see the car hood. Okay.
Understood. When you hit somebody,
yeah,
because the person is going to fall on the
hood. Yes.
hood.
Yeah.
And going to hit the
Bumper.
Not bumper.
Sorry, the hood.
The glass, or
Yeah.
otherwise the wiper.
Yes, yes,
So
yes.
then that's going to be
Yes.
injury. They try to use this.
Yes, yes, exactly. So what will happen is you have, I think this video will show you. So suppose if the pedestrian comes close to the car, okay, so what will happen is the sensors will activate the this mechanism actually, the hood mechanism. So you can see the hood will get engaged and the hood will release so that the the hood will be at a particular location from the this thing actually. So what will happen is your impact, what comes on the, for example, there is a head impact over here. It will be much lesser compared to the hood when it is in the original. So it can cause head injury to the pedestrian, which can cause damage to the pedestrian actually. So to avoid those kind of scenarios, what will happen is when your car is moving at a particular velocity, if there is a pedestrian coming in, in between, in front of you, the sensors will detect it and then the hood will be engaged actually. So that if his head comes and hits on the hood, it will have a lesser impact. Okay, so the energy will be observed by the car hood here actually, instead of the entire vehicle. Okay, that will cause, that can save the life of the pedestrian. So I'll just play the animation once. You can see the animation where the testing is done. You can see the ball coming and hitting on that actually. So entire energy is absorbed in the hood and then this one. So this shows the engaging, how the hood gets engaged. It will be released and the hood comes up actually. Okay. So this was for this particular component, they designed this particular design.
Is it available, sir? In normal available cars, is it available?
Yeah, this was done by for some particular company. No, I don't think so. Yes, yes.
Okay.
It does not have the opening of the band.
Front side.
Which one?
This component does not happen the opening of the band from difference. What to open?
No. It does not affect the opening of the. It will just release the.
When you are working, okay, when you are working, it's here. So you will fall like this.
Yeah.
From here to here, falling is different, whereas the water is coming up or supporting you. Before go having so much velocity and going to hit here, the water is coming like this, so that the amount of
Impact will be less.
It's yet to come into real.
It's like a safety mechanism for the pedestrian. That's. So it will be there in some high-end cars only. Like you will not be finding it in normal cars that we see.
Commercial.
Yeah, commercial cars, we won't see this thing. Coming to this one. So this is that part which is there, and coming to this manufacturing of this part actually. So to how to manufacturing this part. So for example, when we manufacture these kind of parts, we will find issues with respect to distortion, because there are some thin areas or where there's a substantial variation in the cross sections as well actually. So these kind of parts are difficult to manufacture. So what they will do is there can be significant reduction of the initial distortion through AM simulation. What we can do is we manufacture this part, we do some distortion compensation studies, and then we try to reduce some distortions as far as possible, so that you will get a compensated geometry which is ready to print and ready to manufacture actually. Okay. So maximum distortion was cut by half for about 1.5 to 0.75 mm. So using some SimFact simulation softwares, they were able to reduce the distortion during the build and then manufacture the part actually. Okay. So further, AM parts can be within the given tolerance after the first build. So a simulation will help us to reduce the trial and error, which is happening in the back end. Like if you get a distortion at the end of the build, obviously you're losing the material as well as your effort which goes into building the part. And this kind of part can take like 8 hours to 10 hours to build on the machine. Okay, so a lot of effort is involved in building these kind of parts. So simulation will help us to reduce these kind of efforts, so that we use the pre-compensation techniques and things like this to build the part in the first, simulate. I mean, in the you can say with reduced efforts, we try to build the part with reduced tolerances actually, within the tolerance. And this shows some assembly real life build. So this is a base plate on which the base plate will be bolted. You can see the bolted location. Here some holes are there, okay, on the base plate. So this will be bolted with the machine actually. So this base plate thickness, base plate might be similar material, or it might be different material compared to the build material. It will be bolted at these locations on the you can say on the machine. Okay. So this base plate dimensions can be different dimensions. Up to now, the maximum base plate dimension which is there in the in the market might be 400 mm by 400 mm. Okay. Different manufacturers are there for this. Like there are different manufacturers like EOS, then Renisho. So these are all machine manufacturers who are there in the market, who are having these kind of machines actually. So the machines will be having this kind of base plate on which the part will be built. So the part can all the different parts can be built. They build on different areas of the base plate. So to save our time. So what they do is they distribute these different parts in the assembly and build the part like this actually.
Okay, they produce in one shot some numbers.
Yeah, yeah. So here you can see some 3 lower brackets are there and 3 upper brackets are there, which is kept in a different fashion, and you can build this actually. Okay. Later they'll take these parts from the base plate for further processing. That is how it is done in the industry. So you can see some support structures. I don't know if it's support structures or some lattice kind of parts that are manufactured here. So this is another case study where this is something like green team wheel carrier. So wheel carrier is nothing but this particular part, which is something like, which is connecting to your part here. It's something like a race car part actually. Okay. So this study was done by, this is Renisho. Renisho is nothing but a machine manufacturer who manufactures these kind of metal additive manufacturing machines. Then there is a Simufact, which is the simulation company. And then there is a Green Team. Green Team is nothing but they are some student team in Germany. So they are doing these kind of research on these kind of technologies. So they wanted to build this particular part using the additive manufacturing process actually, okay, rather than the conventional part. So this is the this is the the car this thing, and this wheel hub comes within the wheel and then the this thing axle. So this study was done by the student electric team, University of Stuttgart actually, the Germany. Okay. So what they studied is they tried to build the part. They made this design. So this is a titanium actually. Okay. TiAl64. This powder is readily available in the Simufact database. So we can use this database material to build the part actually. And base plate was tool steel actually. Okay. And this is the element size. This is coming to the FEM part, your element size that they use, and number of layers that they use to build the part. Some 82 layers they put to simulate this part actually. And thickness of the support. The support structure is thickness, it is around 0.3 mm. Okay. So this shows the simulation, like complete AM build simulation, then the base plate removal from the base plate. Then after the base plate removal is complete, they can send it to some heat treatment process and so on and so forth. So at the end of it, you will get a part like this, which is, they'll be assembling it inside the car body.
So one doubt sir, actually in additive manufacturing, is there any role of base plate on the produced ones? Is there any role in it?
So the role of the base plate is to that is the whole purpose of the to support the structure. Okay. So, just a few slides. And then they did a correlation, like measurement correlation. So they took some points on the simulated structure and requires calibration for accuracy, enables machine specific prediction. So what they try to do here is simulation. They try to capture some regions where they try to find some distortions here actually. Okay, so this shows this might be a scaled up. It might not be so much distortion. This might be a scaled up things to understand how the distortion can vary with respect to the different location on your model actually. So this is an experimental one. It's a scale displacement by 10x actually. And this is what we are finding in the simulation. Okay. So you can see the distortion in the simulation and the experiment. They were able to so almost match up to a certain extent. They were able to match the values in the simulation and the experiment like this actually. So this shows the different build stage case study. I mean, the cutting from the base plate, support removal, different stages in the analysis. Then you can do a heat treatment to relieve your residual stress in the components, which can happen during the analysis. Cracks driven by high residual stress. So this is also can happen when we build part like these. This red regions that they show is possible separation of the part from the base plate. Okay. So this kind of effects can be simulated. So this shows another case study of this bicycle part getting manufactured using this upper fork that is manufactured using the additive manufacturing. So this shows a software where they use some topology optimization to optimize your part during design, where you can see you can get different designs for your additive manufacturing part. You can see some topology optimization being done there. Okay, where you can use different designs for your topology optimization to build your components like this. So initial design might be like whatever we saw in the beginning, like this. So you want to manufacture a part something like this actually. Using some topology optimization, you would have taken the material and you want to build the part like this. So using traditional method, it might be difficult to manufacture parts like that's where we use the additive manufacturing. So in your this thing Apex tool, you can mesh the component. You can export this as a STL file. You can build your component inside the simulpack like this also. Okay. So this shows the animation of the manufacturing process, how it will happen. Okay, so this is that bed on the which the material will be laid. Powder bed on the material will be laid, and these are the lasers that are coming onto the part. So you can see us slicing. Slicing will be done where each part will be manufactured layer by layer. So once this particular melting is done, these areas are getting melted. You can see the recoater going in, laying. Yeah, you can see the powder getting laid again.
Then another layer.
Another layer is manufactured. You can see that there the fusion will be done again. Like you can see the laser traveling in different patterns. Okay, to manufacture the component. So this will happen layer by layer. It will happen several hours to manufacture the components. Okay, so this shows the animation of that. So you can see the laser traveling in different areas of the base plate. And sometimes in different areas of the base plate, you might get different, distortion because there are some inert gases which are used inside these chambers. Okay, due to the gas flow, what will happen is different regions, different distortions might happen. You'll get distortion different in different areas because effects might be different. Those kind of things, how to capture, we can use some calibration techniques actually, which we are not be. Yeah, we can take those effects into consideration. And this shows a preview of the tool, how it happens. So in Simulpact Attitude, this is a 2020. Right now, we are having the 2023 version, which is installed in the machine in our lab. So we can have a look into that actually. This shows a brief overview how the software might look like creating a project. Okay. So you can get your, CAD model or the STL file inside the project like this. So this will, we will get templates for each machine. Like if you are using a EOS machine, you will get a ready-made template for your base plate or for the EOS machine dimension.
Okay.
Thickness, particular thickness, so that you don't have to make it manually. You can just pull out your machine from the window. You can use the same machine parameters, what they are using in the EOS manufacturing process. Then you import your part. Readily, you can import your part from the your model, whatever design you had modeled in Parasolid, CAD format, any format, you can import the part like this actually. So he's showing how to import the part. So once you import the part, you can see the part will come in the base plate like this. Okay, later you can position your part in whichever we want. You can position the part like this. You can see, yeah, the part will be positioned like this. And in the software, we have capability where we can, based on some parameters, we can see which is your best orientation to build. Okay. So this tool will help you that orientation assistant is there. So based on the support area, based on the, the part area which is coming in with respect to base plate, and based on your design height, all these parameters will be taken into consideration for arriving at a optimum orientation for your part on the base plate. Okay.
It will automatically.
Yes, it will automatically judge it based on the parameters that we are taking. So right now it judges this particular orientation on the base plate. Then what we do is we generate the support structures for the part. So support structure generation, several tools are there. You can use external tools to generate the support structure, or as they have shown here, we can generate the support structure in the SimoPack like this. Okay. So this support structure will be attached to your base plate down. It will be supported, the part will be supported by the support structures. And they'll be having different thickness, all those things, parameters you can set it inside the tool. Then you
Same we can do it in real also.
Yes, the real thing will be done in the manufacturing in your machine. So then you give the material properties for the base plate as well as for the support structure.
If we want to use a different middle for base metals, support means we can do.
We can do so. They have given different options for separately for base plate, support structure, for component. We can selectively use different properties. Then all these parameters we can fit into it. We'll go in detail like during the demo session. I'll choose. You can choose your thing, thermal cycles, everything you can do it. Okay. Maybe we can have a break.
Yes, sir.
And then
We have the break, then we'll go for answer.
Yeah.
So any queries from offline participants? Any queries? Any queries from online participants? In additive manufacturing, simulation? Any queries from online participants? You can raise or you can drop it in the chat box.
Can go to the introduction to additive.
introduction, sir.
Between, I want to tell one thing. Support structure, you are always thinking that we need it. But for complicated shapes, we need support structure. For normal shapes, no need of going with support structures.
Right. And this slide, sir.
What about the plastics?
Yeah, polymers. In SimulFang, we can simulate only the metals. If you are having polymers or plastics, we have a different tool called Digimet, which will use the similar technology, but for the FDM technology, FFM technology, or this kind of polymer-based technologies, no, we have a different tool called Digimet, which has a similar platform for checking the war page, for checking residual stresses, all those things actually. That is it. Maybe we can have a separate session for the Digimet, maybe in upcoming days. If you can give the details, I can arrange a session for Digimet.
Okay, sir. There's some query, whether can someone read it, whether it's a query or some common message which is displayed in the chat box.
Chat. Is there any message?
So that is query and. It's normal, this is the waiting room.
Sir, sometimes we get difficulty in separating the part from the base plate. That also can be predicted.
Yeah, that also can be predicted up to a certain extent because mainly
Actually, separation of part from the base plate is not a big issue, sir. If you want, you can make 2 mm or 1 mm after your machining capacity, you
Yes.
make a layer. Then after that, you start build your own item. So that that particular thickness now it will be removed by any machining process. We go for fine removal, let's engage your specimen. If it is metal, engage your specimen with white DDM.
Yeah.
So flat, you will get a perfect flat with good surface finish, you will cut and you will extract.
yes.
Now the
So
powder,
this, I'll just show you.
okay, sir. For
Just,
powders,
5 minutes.
for powders, we have laser bed fusions, right? Similarly, it machine is itself having the furnace at all. So once you build up the specimen and you can engage directly give how long we need to give the heat treatment. That also possible. So within a single attempt, when you uploaded the material, the file, what type of things you want to manufacture in the STL file, you forget. That's it. They will build after heat treatment, they will give it you back. Then finally, if you want to go for further processing like machining, etc., you can go for it. And also for hip, that is a hard isotope.
We are using FDM for.
Plastics.
It's the problem. Yeah. Plastic different materials
Yeah.
difference. Hip, your SR is telling about hip. The hip we are always using in powder metallurgy, but for our normal educational purpose, we never worried about that portion. We are just taking the powders and compaction. When compaction is over, straight away we put it in the furnace, then cooling, final secondary machine operation needed they're taking. Otherwise, straight away going for supply. But there also one more option is available. We never worried because I also know because I am also from academic professor. So I know that one of the technique we are using.
So recently we did some experiment like this. This is the base plate how it looks like. This is a real base plate where we have printed some samples. Okay, so on this you can see the cantilevered samples getting printed here. Actually. So here this is a setup how it looks in the software. Okay, so what we try to do is we calibrate the whatever printed samples and whatever we are printing in the software. We calibrate such that we will get the close, tolerance levels of our inherent strains, whatever we are getting the real software and the print. Okay. Then what we do is we take out this, we capture these inherent strains like this. So you can see the convergence here. Actually, there will be a convergence graph will come where it will tell you. With the input values from your experiment and with the simulated value, your values are converging. It will throw out the inherent strains which we can use it for our build. Okay. So here different regions. Why I built the samples at different regions is that again due to this manufacturing process, there can be different effects at different regions due to the gas flow that happens inside the chamber. Okay, inert gas are used to prevent some oxidation and things like that in the chamber actually. So because of that, whatever your distortion you might get will be different from what you will get in the edge actually. Sometimes that happens in the reality. So what they do is they print the samples at all the location. They capture all these values at all these different directions actually. And again, why we are printing at different directions because of the orthotropic nature of the material. Like whatever we are printing in this direction, we may not get the same here also. So these kind of experiments we need to do actually to get a parts printed. For example, this is a blade which is getting printed on this. This shows what we this thing printed. You can see the build animation there. Okay, if I play the slide, you can see the animation. After all this, we note down all these things. So this is done on a 3D printing machine like US M400. So M400 means the build dimension, the base plate dimension is 400 by 400. And then the CAD file, STL part is taken or a part file is taken. Then support structure, printing strategy, you can see thickness. Then what type of support structure we are using. There can be block supports, line support, different things are there. Then material, we are using Inconel 718 material, and base plate material is C45 steel, and the base plate thickness is 30 mm. And the base plate temperature and preheating time. So and sometimes the base plate is preheated to a little temperature, so that, as you said, separation of the part will become difficult. So that because of that, they are doing this preheating of the base plate. So that also taken into consideration. And then comes laser parameters. What is the power of your laser? Scan speed of your laser, layer thickness, then hatch style. Different hatch styles are there, like in the machine. That kind of effects also can be taken.
Hashing space.
Hatching strategy. Then this shows the part which is built on the base plate. So you can see the animation, what we normally, we build the part. Okay. And then we see the displacement, what is coming on the part. Different effect on the residual stress. Any requarter contact is happening on the part, which might damage the part as well as it will stop the printing process. In this case, there is no requarter contact. Any possible failures, stress-based failure or strain-based failures. So no critical failures are there. We can study the failure. Then deviation of surface deviation at different location, at different section. What is your deviation? So this is a calculated deviation we took of the part at different location, and we simulated and checked the deviation in the different locations actually. So able to get acceptable deviation. I think this you are not able to see that.
Okay, sir. No problem. Let's see.
Yeah. So that is a measurement we did. So here it shows the, you can see some size sort of deviation, which is, this was happening in the actual part as well. So they were having different difficulty in building this part because of this particular deviation. So this measurements are done in the CMM machine actually.
Coordinate machine.
Yeah. Coordinate measurement machine, where they use the CMM machines to get the deviations.